Okay. All right, everybody, let's get started. Welcome to Lecture 1 here in CE 414 in Steel Design. Everybody in here, I think, knows who I am, so I'm not going to go too down the rabbit hole on introductions. You know, I usually do that whole introduction spiel at the very beginning, but I think every single person in here has had me for class before, so we can dispense with that. Real quick, so just some logistics. On the attendance sheet for this time, I'm asking about the status of the manual, but I am just curious, how many of you have either purchased it and received it, or purchased it and it's on its way? I'm just curious. Okay, good video. Okay, good. We don't need the manual for the first week or so, but after the first week, you'll probably need to bring it every day. And the reason why will become clear as we start getting into the class, but there's a lot of dimensions and details and values that you just really can't do steel design without. In fact, if you actually open up the reference manual for the FE exam, you will find snippets of that in the reference manual because you pretty much can't do steel design without it. But with that, let me not go too far down the rabbit hole. Let's get down to brass tacks. So welcome, everybody. I want to talk a little bit about the operation of the class. I'm going to pull up the syllabus, pull up Blackboard, or the new Blackboard, I should say. I'll talk about that here in a little bit. And then we'll jump right into it. First off, let's talk about grading. So I have elected not to do a project in here. So it's just homeworks and exams and attendance, okay? We're collecting attendance using the QR codes and whatnot, so please make sure that you scan that in at the beginning of class. I am going to do the same sort of homework schedule that I did in structural analysis, sort of those bite-sized homeworks before each lecture. One thing I'll tell you about the homeworks in here as opposed to structural analysis, I think in here they might even be a little faster because unlike structural analysis, there isn't usually a need for a significant amount of diagrams and figures with steel design. That's not to say that isn't always the case. Like you might need to draw out a connection here and there, but a lot of what we do in here is just pretty much straight math. And a lot of the math that we do in here is very much add, subtract, multiply, and divide. You know, the occasional, trig and square root here and there, but nothing really, really intense. This is not one of those classes where you're going to see, you're not going to use any calculus or anything like that. I'll actually show some calculus a little bit a couple times, but I'm not going to make you do any of it. No need to break out Wolfram Alpha to do any differential equation solving or anything like that. It's not like college students do that at all. I don't know what you're talking about. I know things. All right, so one other thing I'll mention is this. This is the AISC Steel Construction Manual. I do know that it's not cheap, so as a result, like you can do steel design without it, but because you have to purchase this, I elect to teach steel design without a textbook that goes along with it. So all of the notes will be made by me, all the homeworks will be made by me, and so on and so forth. So that'll save you some money. And also, even if I wanted to purchase a textbook, it would have been a little, or wanted to make you all purchase a textbook, it would have been a little difficult this time. This is the 16th edition of the Steel Manual, and it just came out. I mean, when I say just came out, I mean it just came out a few months ago. So it would have been difficult to find a textbook that's up to date with the current spec. And there are some things that did change from the last specification. A couple of notations, some material specifications, and also some stuff related to bolts did change a little bit. Now, one thing I will mention is that I put in my email to the class, because I usually get a lot of questions about the manual, and one of the questions that I get is, well, can I purchase a digital version? There actually isn't one out yet. They said that they're planning on releasing the digital version of the manual within the first quarter of this year, so they actually haven't released it yet. That's how new this is. But the reason I mention that in here is because, for the most part, the slides are up to date, but there might be a picture here and there where it's either like I have an old picture or I'm literally physically scanning it. So I'll try and keep it as clear as possible, but I just wanted to throw that out there. let me, before we get into the nuts and bolts of the class, let me, no pun intended, let me pull up the syllabus. Let's see, we'll pull the syllabus up right here. I was just messing around with that. My office hours are Monday, Wednesday, Friday, 1 to 3. But you all know I'm the associate dean, so I'm kind of here a lot more than that anyways. So long story short, if you need me, you can probably get a hold of me. One thing I will say though is that I'm not teaching class Tuesday and Thursday. So there might be a Tuesday and Thursday where if you need to get a hold of me, we might have to have a quick Teams chat or whatnot because I might not be on campus. But that's probably not going to be the case for the days this week. You woke up, you're here. You made it to class, whoever alarm went off. I will mention, let's see, what else? Oh, I am teaching, I don't have it here on this syllabus, but I will mention this. I'm teaching CAD for the first time this semester, and we meet Mondays and Wednesdays from 11 to 1. So I have 2 sections, one from 11 to 12 and one from 12 to 1. So one of the things I'm going to tell the CAD class is the Friday time period from 11 to 1, I'm sort of reserving just for them because I got a lot of students in there. I got about 120 students in there, and so that means that that's a lot of students with potential homework issues and software issues and things like that. So I'm sort of making myself Friday available for them just for that time slot, if that makes any sense. That's not to say I'm not free, but if you try and get a hold of me like after class on Friday, that might be why I might be booked and whatnot. Okay. When it comes to the manual, I will say just formally, if you have not yet purchased it by this week, you really should. Because like I said, after week 2, we are going to use it pretty regularly. Now, I'm going to give you a homework assignment on Friday that's basically just making you open the manual up and look up some values. It'll take you like 5 minutes. That'll be due the Wednesday of week 2, like after we come back after the Martin Luther King Jr. holiday. Now, if you're in a boat where you've ordered your manual and it's late or it's still in the mail, like let me know because I'm going to be pretty kind on like late penalties and things like that with that assignment if you're still waiting on the manual to come in. I'm not going to hold your feet to the fire because of delays with the post office. But just make sure that you're keeping me apprised on that. Okay. I do want to pull up the class schedule. So I do want to mention a couple of things. And this really did sort of, I don't want to say annoy me, but I had a really nice class schedule where the week before spring break, we would have class on or review on Monday. We have an exam on Wednesday, and then I would give you the Friday before Thanksgiving break off. But unfortunately, the spring break is a week later, okay? And unfortunately, like I can't just not do anything with that week. So I am going to start columns right after our connection assignment. But I am still going to go ahead, assuming everything goes well with weather and everything like that, I am going to try and cancel class that Friday before there I said it again, right before spring break. What I will probably do is, if you notice on the homeworks, I'm going to have a homework due that Friday that you can submit virtually, but I'm not going to have anything assigned during spring break. I want spring break to be just that, a break, okay? All right. Now, like I said, so I do these, the daily, homework assignment thing that I do in the past, like I've done instructional analysis and things like that. But again, the homeworks are really, they're pretty short, and you'll start to see this. Like our first homework assignment will take you no more than 5 minutes. It's not a very difficult assignment, and you'll see what I mean when we get into that. I try and make sure there's buffers around exams and things like that, but I think you'll find that if the homeworks and structures were maybe cumbersome at times, I don't think you're going to find that's the case in here, or it won't be as bad, I'll say. Exam dates are going to be somewhat set in stone. So our first exam is going to be Friday, February 9th, and then our second exam is going to be Wednesday, March 6th. So before those days, we will have an exam review where you come in, ask whatever questions you want, and then we come in and we celebrate on those days. Assuming weather cooperates, this will pretty much be our schedule for the semester. We will have a final exam during exam week. We drew a somewhat short straw because it's on the Friday of exam week and it's at 8 in the morning. My apologies there. But I will say that the exams in this class are not comprehensive. And if there is any class of mine that I teach where the exams are not comprehensive, it's this one. This is a very modular class. We learn a topic and then we move on to the next one, and we learn a topic and we move on to the next one. And so they are very modular in nature. There's always a little bit of bleed over of material from one topic to another, but in here it's pretty minimal, especially between exam 2 and exam 3, because columns and beams are way different than connections and whatnot. The exams are weighted a little differently. So if you look at the exams, exam 1 is worth 20%. And instead of making these two both worth 20, this one's worth 15 and this one's worth 25. That's just because of the nature of what's covered on the exams. Exam 2 is the bolt and weld exam, and it serves very nicely to sort of isolate bolts and welds into a single test. Because if you took bolts and welds and added columns, or bolts and welds and add tension members, that would make for a really, really big test. Okay, and I don't want to do that. But exam 2 is gonna be the easy one. Not only is it gonna be easy, but it's just not gonna cover that much material. But columns and beams, that is kind of a heavy topic in terms that it covers a lot. So it is worth a little bit more. So it's not so much for difficulty, it's for the amount of content covered on each exam. Okay. The only other thing that I'll bring up is Blackboard. So let me open Blackboard if it'll load. Let me refresh this. Oh, I'm not connected to the internet. That would explain. Let's try this again. Because I don't know, has anybody looked at Blackboard, or has anybody had any classes with the Ultra Blackboard? I hate it. I got to be honest. This is what Blackboard looks like now for the class. So it looks really different. So what I would say is that for you, let me turn on student preview so you all can kind of see what it looks like for you. What I would say for you is that it probably navigates a lot nicer. It's more mobile friendly and things like that. I'll admit, for me, it's not very fun, but I'm getting used to it. Right now, if you log in, you'll see a link to the YouTube playlist. You'll see lecture notes that go up through the first few weeks. And then just like in previous semesters, as homework assignments come through, you'll see them pop up here. A couple of things that I want to mention. The first thing I'll mention is this attendance link right here. So the new Blackboard wants you to log attendance a little differently. I have not yet decided if I'm going to do it like this or I'm just going to manually upload it. We'll see, but I'll make sure that the Blackboard is current with the course calculation. The other thing I'll mention is in here in lecture notes and supplements, there's topics for, so we have here topics for each of the fundamentals, tension members. So if you open up topics, you'll see, here's all the lecture notes here. If you look here, you'll see all the lecture notes there. I did want to mention the AISC errata tab, because there's two things in here which I'll highlight later because I kind of want to get into the notes and whatnot, but there's two things in here which I think are worth mentioning. The first is the specification. So this is the manual, and we'll talk about this in more detail a little bit later this week, but this is the manual, and most of what you're buying when you pay for it is a lot of design aids and tables and design tools to help you select members, select connections and things like that. But this material here in the back, this stuff, you can kind of tell you're in the right spot because there's these like gray pages on the side here. So it's basically this part right here where it has like white and gray. This is the specification. This is the document. This is sort of the law, as it were, that actually defines how you design and detail steel structures in the United States. And that's sort of the law. That law document is free for download. So I posted that onto Blackboard. The other thing that I have posted is an Excel file which contains all of these dimensions. The W shapes, angles, channels, all those dimensions are free for download as well. So if you open up AISC errata, they're in there. Okay, it's not to say you have to use them. I just threw them there in case you want them. I also have a link to the playlist, and then the syllabus is here on Blackboard as well. Okay, before I move on, let me see if anybody has any questions. Does anybody have any questions just about course operation? I figure most of you have had me before, so this isn't anything that should be all that new or all that different? Everybody good? All right. So let's talk about this class. Let me take a step back. So everybody in here is required to take structural analysis, and then you have some electives, and you have some options for taking electives in structural design. And I want to talk a little bit about what structural design means, okay? I'm going to try and paint the context of what we did last semester into this, but I think the best way of starting is to take a step back and talk about what actually is structural engineering. I think you all can probably do a pretty reasonable job of defining what civil engineering is, as it's your major. But as you know, civil engineering has various disciplines. It has geotech, transportation, environmental. So what's structural engineering? And so you could probably find a bunch of different definitions for what structural engineering is. You could abridge it. You could find some long-winded one. I would say that structural engineering is the science or art, or science and art, of designing structures so that they could safely resist the forces to which they may be subjected. That's structural engineering in a nutshell. Okay? So, for example, and I've used this example quite a bit in this room. So we're in a classroom. If we look here in the roof, if we sort of conceptualize what's going on above this drop ceiling, I can see a column right here, probably a similar column back here. So there's probably a beam stretching in this direction that's supporting the load of the floor above it. Okay. So what we would do in structural analysis is we would try and capture those loads, right? And there's a number of ways that we could do that. If it was a truss, we'd have method of joints, method of sections, shear diagrams, moment diagrams, all those nifty little tools we learned last semester. Basically what we're trying to do is quantify this, the loads, the forces that the structure is subjected to. And those forces come from the self-weight of the structure, what the building's being used for, the environment, so like wind loads, snow loads. If we were out in California, we'd be worried about earthquake loads and all of that. What we're going to be focused on primarily in this semester is this, the resistance, how strong the structure is. That's a function of what the structure is made out of. Is the structure in tension? Is it in compression? Is it being bent? Are we talking about bolts? Are we talking about welds? What are the, and I'm going to throw this term out here, limit states. We'll talk about limit states in more detail here in a little bit, but what are the limit states that we are considering? But to be clear, as long as our resistance is greater than or equal to our loads, then the system is fine. You could think of it in economics. It's like as long as your supply exceeds your demand, you're good. It's kind of the same idea. As long as the resistance, how strong the structure is greater than or equal to the loads that the structure must hold up, that's it. That is structural design in a nutshell. I don't think I could simplify it any further. Okay? We structural engineers, we tend to walk a very fine tightrope, though, because I mean, there's a funny saying that anybody can design a bridge, but it takes an engineer to barely design a bridge. It's a little bit of a tongue-in-cheek way of saying it, but there is kind of a point to it. I mean, if I'm designing a bridge, let's say in the Barbersville area, that's going to be carrying traffic, and I know my grandma's going to drive over that bridge every day to go to the post office and go to the grocery store, and I think, well, goodness gracious, nothing's happening to grandma, so I'm going to make that bridge incredibly massive, super deep beams, tons of reinforcement, all of that. There is a problem with that approach. Sure, I have created a structure that's probably safe. I don't think a nuclear bomb would move that bridge. But then the problem is this. The problem is it's too expensive, okay? And, if we're talking about bridges, who pays for bridges? We do, right? The taxpayer. But whether or not we're working for the public sector and the client is the taxpayer, or we're working for the private sector and the client is just that, like a person or a company. I mean, the same thing applies if I'm designing a bridge or if I'm designing the corporate headquarters for an insurance company or whatnot. It doesn't matter. I still have to walk a tightrope between safety and economy. Whenever we design structures, we cannot violate safety. The safety, health, and welfare of the public is our foremost concern. But then when we get past that, we have to consider the economy. providing a structure that, or providing a system that is the most, or is as economical as feasibly possible, or what have you. Now, I do want to introduce the idea of a limit state. So what is a limit state? A limit state, so you're going to hear me use this term a lot. And certain members are going to have more than one limit state. So for example, when we start looking at tension members are going to be our very first sort of real module in the class. And tension members are when you take a piece of steel and you yank on it, okay? A limit state is basically asking what are the different ways that that tension member can fail, okay? Or more specifically, what are the conditions that we can define for that tension member such that should those conditions be exceeded, we're going to consider the member not in compliance, okay? So, for example, if we take the tension member, okay? So a tension member is me taking a piece of steel and yanking on it. There's a couple of ways that that member could be deemed to fail. One of them is going to be called yielding in the gross section. One of them is going to be called fracture in the net section. What if the member is fine and it's the connection that fails? Maybe the bolts fail or the weld fails. Maybe there are some other connection-related phenomena that we need to consider, and what have you. And we could go on and on. For a general member or a general system, we tend to split limit states up into two broad classes. The first is what I would call strength limit states. Strength limit state or a safety limit state. A strength limit state or a safety limit state is sort of what it essentially means is if you have a member and you violate that condition, you're putting people in danger. Okay, you are at a point where the safety, health, and welfare of the public is compromised. Okay, so a good example of a safety or a strength limit state would be, for example, if we're talking about a column, a strength limit state would be buckling. Okay, if the column buckles, we're in trouble, right? That's bad. Okay, that is a strength limit state. Another limit state to consider, or another type of limit state or class of limit states, are service limit states. Service limit states are not about the structure falling down and killing people. Service limit states are more about ensuring that the structure performs well on a day-to-day basis. I'll give you an example. How many of you have ever been in a building, a house, what have you, where you looked at the roof and the roof was plastered? How many of you all have ever seen that before, like a plastered roof? I'm sure most of you have, okay? Well, so if you're looking at the beams, a common service limit state is to take the length of the beam, divide it by a certain number, let's say 360, that's L over 360 is a common deflection limit. So let's take L over 360, so we take the length of the beam, we divide it by L over 360. So if I have a beam and I divide it by 360, I'm probably going to get a distance that's about something like that. Like it's going to be a really tiny number, right? So one of the service limit states for beams is that we say if you have a beam, it can't deflect more than that much under live load. And you go, well, why is that? Because if you deflect more than that, you crack the plaster, okay? Now, if you're in a building and you see some cracking on the plaster of the roof, it does not mean the roof is going to fall down and kill people, okay? But it does mean that the roof is not performing its intended function. Like, I don't want to have a roof where I put some people on the floor above and the ceiling cracks, right? The plaster cracks. I don't want that to happen. So I need to provide beams that are stiff enough such that that doesn't happen. So it's possible that you may be in the process of designing a beam and you might do the math and you might see, okay, I need a 8-inch deep beam to be safe, but I better use a 10-inch deep beam because if I use an 8-inch deep beam, it's not going to be stiff enough to prevent the plaster from cracking. Does that make sense? So there are a series of limit states that you might need to assess, and then you pick the one that controls or the one that governs. And I'm using a lot of terms here like controlling limit states and governs. Don't worry, when we actually start, getting down to brass tacks and actually doing the math, you'll see how we're able to take our time and digest these terms a little bit more easily. I should mention, and I mentioned this on day one. It's funny because some of this stuff I mentioned on day one, and some of it we're never going to talk about again. But I do want to mention the real world. We as structural engineers do have requirements that are somewhat beyond the just raw safety and service conditions. It is not out of our scope usually to produce a design that is aesthetically pleasing. We usually will work in tandem with the architect or the client to ensure the needs are met. And I'll sort of explain what I mean there. So if you were to go to an architect and you were working for the architect to, let's say, design a convention center, and the architect says, I don't want any columns throughout the entirety of the floor, so I want an open space that's like 300 foot wide on every side, and I want the roof to only be this deep. There's this thing called physics, and that's not going to work, okay? Now that doesn't mean that as a structural engineer, you can just totally say, well, that isn't going to work. You need to work with the architect and the client to develop a system that's going to make sense. It's not that unheard of to go into, let's say, a convention center and see super big open spaces, right? That's common. But look at the roof, right? The elements that are supporting the ceiling are really deep. You want a good example of that? Go to the rec center, okay? Go to the rec center and look at where the basketball court is, okay? Okay. Now think about that space. That is a huge, wide open space. No columns anywhere, right? But look at the roof. You see those trusses up there? They're huge, right? They're super deep trusses because that is a long span to support a lot of load, right? Now, what happened was the structural engineer needed to work with the architect, work with the client to ensure that those roof elements were going to be able to support that load safely, right? But it didn't mean they ignored it. I mean, how much credence would the structural engineer have if they went to the client and said, yeah, we're going to need columns right in the middle of that basketball court? Like, no, gotta have a basketball court open, right? Does that make sense? So you gotta work with that. Another thing that we have to consider is constructability. There are actually some limits that we are going to rawly apply, I guess I would say. For example, we're going to be sizing and detailing bolted connections, okay? And so one of the things that we're going to have to determine is how far apart bolts can be spaced, okay? So let's say that I've got a 3/4 inch diameter bolt and a 3/4 inch diameter bolt, and I place them like right next to one another. I mean, we're talking like bolt here and bolt like literally right next to it. So here's the bolt, here's the bolt. Does anybody see a problem from a construction standpoint? Imagine trying to get a socket wrench around this bolt, right? It's knocking into this one, right? So the bolts have to be a certain distance apart so that you can actually get a wrench around it and tighten the bolts, right? There is a minimum bolt spacing, okay? What about, what happens when the bolts get too far apart? Well, if you have two plates and the bolts are really, really far apart, when you tighten those bolts, you're going to get a little gap between the plates. And what can get in between that gap that steel is really going to hate? Well, what causes rust? Water, right? So if you don't have enough bolts to ensure a tight fit between the plates, you could get water in between your plates, and that could cause corrosion, right? So while we may not handle this directly, there are some limits that we do need to consider in that regard. Now I do want to mention this. This is more of the business side of things, but there's also the engineering aspect of it too. I have here, these are some really conceptual conceptual layouts, but these plots, I think, are really kind of important to illustrate to you the role of different stages of a process in an engineering project. This left chart shows your ability as an engineer to impact the cost of a project over time. So let's say it's the design of this building or the design of the new business building, okay? At the very beginning stages, when they're planning the building out, when they're generally getting an idea of how many square feet the building's going to be and how many floors there's going to be and so on and so forth, there is a real significant ability to affect the project cost over time. I mean, for example, let's just take the conceptual planning stage for that new business building, the Brad Smith building. If somebody on day one said, let's just add a couple floors to the top, let's just make it a 10-story building. Now that's a easy decision to make when you haven't built anything yet, but how much money do you think that decision was? That's a lot of money, right? That's a strong ability to affect cost over time. If somebody had went to the contractor 4 months ago and said, yeah, we need to rethink some things, well, it's a little late, right? The project's already done, right? You don't really have much ability to influence cost once they're putting the roof on, right? It's pretty much done at that point, okay? But on the flip side, the nice thing about it is conceptual planning is cheap, right? Design is cheap compared to the construction project. But you also need to have some serious respect for what's going on during these initial phases. Because if you get to the point where you're erecting the structure and you find yourself a problem, that's going to cost some money, right? So you as the engineer need to be aware that those initial stages of planning a project and planning your solution have a very significant impact on overall project costs, okay? Does that make sense? All right, I do want to at least maybe kind of introduce some stuff in our second lecture because you're here, and I want to try and get into this, and I want to talk about this idea of a limit state, and I kind of want to talk about design philosophies. Okay, that is a very fancy term, but it's a really simple idea. Okay, so I'll skip past this because this is assuming we're talking about this on Wednesday. So. We all kind of hopefully kind of get an idea about what a limit state is. I want to talk about a factor of safety. Does everybody here know what I mean when I say factor of safety? Right? Okay. So, in case you don't, let's keep it real simple. Okay? Now, I am going to use, here's what I'll use as an example. Let's use these tables in this room as an example. So let's take this table, okay? Let's take this table, let's say I'm feeling pretty destructive, okay? So I want to know how much this table can hold up, okay? So I go down to the lab, I put this on a testing frame. Anybody ever seen like the hydraulic press channel on YouTube? You know what I'm talking about, where they put something in there just right? Let's just do that to this table, okay? And let's make up a number. Let's say that I put that on the hydraulic press channel, and then at around 800 pounds, I know that's a high number, but let's just use it because it's a nice number. Let's say at 800 pounds, that table snaps in half, okay? Do I tell you as a consumer that 800 pounds is how much that table can hold? Probably not, okay? Instead, what I'm going to do is I'm going to back that off a little bit, right? Let's say I use a factor of safety of 2, right? So instead, if its actual capacity is 800 pounds, I might say its allowable capacity is 400 pounds, like half it, 800 divided by 2. Now, I'm talking about that with resistances, right? I could very easily flip the script and talk about loads, right? Because I could say, I want to be able to sell a table that holds up 400 pounds. So I'm going to design that table to hold up 800 pounds. I could do that too. I could either magnify the loads or decrease the resistances. The effect is the same, right? It's the same idea, okay? That is a design philosophy, okay? In other words, I have calculated loads and calculated resistances. And what a design philosophy basically means is I am adjusting those loads and resistances to achieve safety. That's what I mean when I say a design philosophy. And the simplest design philosophy ever is a factor of safety. Okay? Which, by the way, just blanket factors of safety are still used. A good example of where they're used is in the land of geotech, right? In geotech, soil properties are so variable from place to place that it's a little bit more difficult to be a little bit more scientific than that. Whereas in a land like steel design, steel is a manufactured product, so you can be a little more scientific about it. Okay. Everybody get the idea there? Okay, so the name for that design philosophy, we have a specific name for it in steel design. We call it allowable strength design, or ASD. Sometimes you might call it allowable stress design, where it's allowable stress design, allowable strength design, same thing. So whenever you hear allowable stress or allowable strength, I just really want you to think factor of safety. That's basically what it is. Sound good? Now, let's go back to the tables. How much did we say this table broke at? 800. 800. Let's say I'm feeling pretty destructive. Let's say I can get the hydraulic press channel down here and I break this table. Is this one going to fail at exactly 800 pounds? Exactly? No. Let's say I'm feeling real destructive. I have to break every table in this room. That you all wouldn't like me because you wouldn't have a desk. But let's say I was feeling pretty destructive and I just broke them all. Are they all going to break at exactly 800 pounds? No. This one might break at 790. This one might break at 805. This one might break at 782. That one might break at 806. That one might break at what have you, right? And I could collect data on all the tables. Like if I repeated the experiment 100% as scientifically accurate as I could be, I'm still going to get some scatter in that data, right? Now, why am I getting scatter? Why am I getting different answers from different tables? Why am I doing that? Well, let's look at this side. These tables are made of wood. Are you telling me that this organic plank of wood is going to have the exact same 100% exact properties as this plank of wood? This organic product? The same as this one? Same as this one? What about the fabrication aspect? These, even though the holes and the little peg slots and what have you in these tables were probably drilled by a machine, are you telling me they're all to within 100% exact, that there's no machine tolerances there, that those holes aren't to the same position plus or minus a millimeter or so? Now, I can tell you this, these tables, if I was a betting man, probably came in a box. How many of you have bought furniture like an entertainment center from Walmart or a bookshelf from Walmart, like the particle board, you put it together, right? Are all of those nuts and bolts to the exact same torque? You're telling me that you mean to tell me there's actually a human aspect to the fact that if you buy a bookshelf and you buy the same bookshelf and you both put it together, that they're going to be put together a little bit differently, even if you're both following the directions, right? Because I know engineers, they take the instructions and they throw it away, and I can figure this out. I know what I'm doing. I'm an engineer. And then they look and there's part AF and plank B, and they're like, what do I do with this? And they get the instructions, and then they don't tell anybody that they got the instructions. I did it all myself. Is there any familiarity to the story? You're looking at me like, yeah, I know there's somebody that did that. Okay, back to topic. In all seriousness, one of the problems with allowable stress design is that it fails to address uncertainty in a very real setting. Okay? So instead, what we're going to do is address uncertainty a little bit more scientifically by looking at both the resistances and the loads separately. Okay? When we look at resistances, there are uncertainties associated with them, with material quality, with fabrication tolerances, with construction practices. There are also uncertainties on the load side of things. For example, one of the loads that we have to design structures for is us, the people in this room. And there's variability in the occupancy load of this room. There's going to be variability in your ability to estimate wind load, to estimate snow load. How accurate is your analysis method? You remember probably on day one of structural analysis, I said we're not really analyzing structures. We're analyzing mathematical models that represent structures. And there's some accuracy loss there, okay? So there's uncertainty associated with both the resistances and the loads. And so if ASD says, let's just take the whole problem and use a factor of safety of 2, LRFD says that's not what we're going to do. Instead, with LRFD, we're going to factor the loads and the resistances separately. We're going to factor them differently. We're going to use different resistance factors to decrease our resistance, and we're going to use different load factors to amp up our loads. Okay? I'm going to actually sort of stop it here because I don't want to information overload you on day 1. But what we're going to do is we're going to come back to this on Wednesday, and we're basically going to say, okay, let's talk about the different types of loads that structures see. Let's talk about how we estimate them, how we categorize them, how we quantify them. If you remember in structural analysis, we had sort of defined dead loads and live loads. I'm going to redefine them, not totally, but in a little bit of a more easy to digest light. In other words, no influence lines, because I know influence lines are tricky, right? We won't worry about that. But I'll come up with a different way of defining those, and we'll talk about environmental loads and some things like that, and then get into some load combinations and what have you. I kind of want to stop it there. I know we're ending a little bit early, but I don't want to overload you on day 1. I don't have a homework for you today, unless you want one. There we go. I had one person shake their head no. Okay, I am going to stop the recording, pull the code up one more time in case anybody needs it, but I will see you all on Wednesday.